Electromagnetic Spectrum. Cut out every box and cut out every picture. Okay? This one's very different than all the other journal entries we've done so far. We're actually going to reorient the entire journal. So the page number, go ahead and write it really small in the upper right corner. And write up there, electromagnetic spectrum, really small. Sorry, you can't hardly even read that. We're going to rewrite that title in just a minute. We're going to completely reorient the journal. Okay? So take your journal. You're going to turn it like this. Okay? So that this part, your front cover and all the pages you've done so far, are up, and the bottom is down here. Okay? So there's your title, normal page number place, oriented this way. Okay. Now, what is the red line is now going to mark the top of the page. Okay? And up above there, go ahead and write in the title nice and big. Electromagnetic Spectrum. Okay? So electromagnetic spectrum. Spectrum is anytime you have a whole bunch of things that are similar or related, and you're just putting them in order from like smallest to biggest sort of thing. So if I were to take all of you students and line you up from the shortest person to the tallest person, that would be a spectrum of student height. Okay? So the idea of a spectrum is just a whole bunch of things that are the same. You just put them in order from like smallest to largest. Okay? So the electromagnetic spectrum, these are all different forms of light. Okay? You'll hear that said often. Technically, they should be called electromagnetic radiation, but a lot of times they'll just be called light. So I just want to put that in there so you guys know. People often refer to these as different types of light. Okay, so we're going to do this in order starting, because it's a spectrum, we're going to do it in order. We're going to start at this end, which is, if you look at your page, it's like the bottom of the page. All right, this is going to be the left side. We are going to start there, and we are going to talk about radio waves. So find a little piece of paper that says radio waves. Get your glue and just a little tiny drop of glue and glue that in. Okay, I've got to get a different glue bottle. One second. Okay, everything we're gluing in today is going to be fairly small, so you're going to want to use very small drops of glue. Okay, so radio waves. A little bit of glue. You're going to glue it as far to the left as you can, right below the red line. Okay, so radio waves. You've certainly heard of radio waves before. What are radio waves used for? Everyday application for radio waves.
Your car radio?
Hmm?
Your car?
The radio in your car. All right? What do you usually listen to through the radio in your car? Music. Okay, so that will first give you an idea of what picture we're going to use. All right? And I'm looking for the words. Communication and music. Okay? Radio waves are a very common use of communication. More of the previous generation. All right? So like handheld radios, stuff like that. They're actually really good for communication. And hearing music. Okay? So the radio has an antenna to receive that signal. That signal comes in the form of a radio wave. Okay? So go ahead and glue that picture of the radio in as well. Now, once you've glued those in, those 3 pieces of paper in, I want you to get your pen or pencil and draw in a dark line to separate it from the next one. Okay? So within the spectrum, there's all of these different sections. The radio wave section, there's a lot of different lot of different waves within that. It's just a section of the spectrum, okay? And it's the what we call the low end of the spectrum, okay? Next in the spectrum are microwaves. Go ahead and glue in microwaves there next to radio waves. All right? Microwaves are a little bit smaller and a slightly higher energy, okay? And microwaves are used for two primary purposes: heating water and cell phones. The signal used in cell phones. So a lot of our modern communication, Bluetooth, cell phones, and things like that are actually in the microwave range. Okay? Those are actually fall within the microwave range. Okay? Now, interestingly enough, okay, remember we talked about water molecules, okay? I'm going to give you guys a little side visual here. All right? Water molecules, remember we talked about kinetic energy of molecules, and that tells you about how hot they are, okay? Remember that? So, water molecule, bless you. A water molecule, okay? The length of a bond between the hydrogen and oxygen is this very specific length in a water molecule. Microwaves, when they hit that bond, the energy gets absorbed. And then all of that energy absorbed, that water molecule starts vibrating like crazy, which means it becomes very, very hot. This is how your microwave oven works. It's an energy transformation. We're going from electromagnetic radiation to thermal energy. All right? So we're going from one electromagnetic radiation to radiant energy to thermal energy. Okay? It's an energy transformation that happens. The way they discovered this, actually, scientists were working with microwaves in a laboratory, and a guy had a chocolate bar, like a Hershey's chocolate bar, in the pocket of the front pocket of his shirt. And after working in front of the microwave generator for a moment, the entire chocolate bar melted, and he's like, "What on earth? Why did it melt?" And they started playing with it. They put an egg in front of the microwave generator, and it exploded. They put popcorn seeds in front of it, and they started popping. Okay? They discovered that this energy transformation was happening, and they figured out it was in the water molecule. Okay? So the picture that goes with that is hopefully a little obvious. Okay? This is actually called a microwave oven. Okay? It is used for cooking. It's an oven. But it uses microwaves to heat the water in your food. Okay? So everything you eat has at least some sort of water in it. A little bit or a lot, depending on what it is you're eating. Okay? So if you put it in the microwave, it heats up the water molecules. That water molecule, by conduction, heats up the rest of the food. Okay? So interesting real-life application. If you have pizza, someone puts it in the fridge. If you don't put it in a bag, you leave it in the box, and you put the whole box in the fridge. The next day, your pizza's kind of dry, right? Try and heat it up in the microwave. Doesn't heat up very evenly. Part of it's cold, part of it's hot. Not very pleasant. Okay? Here's your special little hint. If you know how a microwave works, you can heat your dried food better. Okay? So you take your slice of pizza, you get a paper towel. You get the paper towel wet, you squeeze all the water out of it, and then you wrap your slice of pizza in a damp paper towel. You put it in the microwave, 25 seconds later, perfect pizza. It'll be almost like the pizza was only just cooling down for the first time. It works pretty well. Give it a try. The next time you have dry pizza at home in the refrigerator that you don't want to eat because it doesn't taste very good, even if you heat it up, try it. It will work. Okay? All right. Because the microwave oven heats the water molecules in the paper towel, that evenly heats the pizza if you have the whole slice of pizza wrapped in the paper towel. Cool? All right. Next topic. All right, next segment of the electromagnetic spectrum is infrared. Go ahead and glue that in. Okay, infrared. So so if someone says infrared, where have you heard that before? Where have you heard infrared before, besides my class?
Lasers?
Lasers? Cameras? All right. What kind of camera?
Night vision.
Night vision. Usually when I say infrared, someone always says some like video game where they have the goggles. Infrared, yeah, and some people are smiling out there. Yeah. So the infrared goggles, okay? You can see at night. Night vision. All right? And heat waves. So the way those night vision goggles work, okay, is the fact that they can see infrared. Our eyes do not detect infrared, but it is just another form of light. And you can adjust a camera so that it sees the infrared, which is heat. All right, remember I talked about conduction, convection, radiation? That's where I've talked about infrared before. Heat traveling by way of radiation is in the infrared spectrum. Okay? So, the picture I've chosen is this one, which you probably can't tell what it is until I explain it to you. Okay? So, don't glue it in yet, but what you have there is a trash bag pulled over a guy. Okay? What you see right here to the side, there's an infrared camera being pointed at the guy under the trash bag, and this is what you see on a computer screen next to him. That's what the camera's seeing. You can see his fingers right there. You can see his head, his shoulders. You can see the outline of the guy through the trash bag. Okay? So, who would benefit from what animals, obviously we don't see this, what animals would benefit from this? What animals would benefit from this? Nocturnal animals. They hunt at night. So if you were an owl, and owls eat like rats and mice, and you're out flying in the dark, guess what? You can see mice glowing in the dark. They're almost like they're glowing, okay? You can even see them even if they're hiding underneath the grass. You can still see them because they're hot. That infrared heat that infrared radiation passes through the grass. It passes through things, just like it does the plastic bag, and you can see things glowing in the dark. All right? Infrared vision goggles, really powerful ones, can see through certain solid objects. Okay? Does it make sense? So like clothing and fabric, it sees right through it, no problem. Okay? So that's why I chose this picture. Now, to glue this one in, you have two options. You can either fold it in half and glue it in like that, or you can turn it sideways. I prefer to turn it sideways and trim it a little bit, but I wanted you to see it before I wanted you to know what it was before you decide how you want to put it in. Okay? So I'm just turning mine.
Excuse me.
Yes?
In Lule, you have Carolina Gonzalez.
Yes?
Can you send her to her friend office? She's in for today.
Okay.
Thank you.
All right, after infrared vision, you can draw in that dark line, and now we are going to talk about the next segment, which is the middle segment of the electromagnetic spectrum. And the one most important to us, visible light. Okay? So, when something says it's visible, what does that mean? It means we can see it. We, as human beings, are capable of seeing this. Okay? That is the colors of the rainbow. We are capable of seeing the colors of the rainbow. The picture for that is the eyeball, because I'm trying to emphasize that it's something you can see. It's the visible spectrum, okay? Visible to humans. Like I was saying before, nocturnal animals, like the owls, their visible range is in the infrared and in our visible. So this is our visible range. Theirs is actually shifted over this way. Okay? Does that make sense? So they see differently than we do. They don't see everything we do. We don't see everything they do. Okay? So visible light, going to go ahead and draw on the dark line. We'll come back to visible light in a minute. No, actually, we'll do it right now. Draw on that dark line on the opposite side of visible light. We are going to get into more detail on that. So, this is where it gets a little complex. Everybody pay close attention. Take the bottom of your paper. All right, what is the bottom of the page there? Okay. Take that, fold it up so that it comes right underneath the words. And crease that. Okay, we are going to talk about the colors of the rainbow. So, those two really dark lines on both sides of visible light, we're going to expand that. Right now, like this. And just do a little, like, bracket thing over here. Both directions. Okay, I'm going to expand that in both directions. All right. Now, the visible light, the colors of the rainbow, okay? If you want to, go ahead and glue in the picture of the rainbow there. Right in the middle. All right, so here we go. Here's a challenging question. Does anybody know the colors of the rainbow in order? All right, some of you have learned it. Red, orange, yellow, green, blue, indigo, and violet. Okay? Now the reason why we know that is because of an acronym. Take the first letter in each one of those words. And it makes like a guy's name, Roy, little middle initial G, and then Biv. Kind of a weird last name, but it helps you remember them in order. You do need to know those in order for the quiz. Okay? Now, something I want to kind of focus on here for a moment. Infrared. Over here, beyond red, I want you to write infrared. Underline infra. Squiggly line underneath red. Infra means below red. That's where it got the name. Infrared is just below red. Okay? Over on this end, beyond violet is ultraviolet. Ultra means above violet. Okay? So visible light, the next section is going to be ultraviolet. Go ahead and glue that in. Ultraviolet, more commonly referred to as UV light. Okay? More commonly referred to as UV light. What do you know about UV light? It's from the sun. All these come from the sun. In different quantities, but all of these do come from the sun. What is ultraviolet light? Good? Bad? What does it do? It gives you sunburns. Ew, that sounds unpleasant. Okay? It can give you skin cancer. Ooh, that's even more unpleasant. And then it says there on the little piece of paper, vitamin D. Wait a second. Vitamin D? Vitamin D sounds like a good thing, doesn't it? It is a good thing. Your body actually makes vitamin D using ultraviolet light. You eat part of your food that has what it needs in it, and then as your skin gets radiated, vitamin D is formed. Okay? Vitamin D is essential for healthy bones. You'll find it added to milk. Vitamin D combines with calcium to produce healthy bones. All right? But they added it to milk just to make sure if you're not getting enough sunlight, at least you still absorb the calcium in your milk. Okay? So it's been added to milk. It doesn't naturally occur in milk. Okay? So, picture for that. Going with the guy putting sunscreen on to avoid the sunburn. Okay? Sunscreen is a good thing. All right, you do need some light every day. In Laredo, where we're fairly close to the equator and we get pretty sunny days, you only need about 5 minutes a day. If you live up in Alaska, it's like 30 minutes a day of sunlight exposure to get enough vitamin D to maintain good health. So 5 minutes in the sun every day, you should be good. Otherwise, wear sunscreen. Okay? Because too much of it, too much exposure over a long period of time, even if you rarely get actually sunburned, you just keep getting a little bit of sun every single day, you're going to probably have a high risk of skin cancer. Okay? Now, the lighter your skin is, like mine, the higher the risk of sun cancer. The darker the skin, like my husband, less risk of sun cancer. Less sun gets in. That's what darker skin is for. It's designed to block out the excess ultraviolet radiation so that you don't get skin cancer. You can tell my ancestors came from the north, where there's not a lot of sun. Okay? My husband's ancestors came from the equator, where there's lots of sun. Okay? Yes? Does that make sense? All right. All right. After ultraviolet, we now have X-ray. What is X? When I say X-ray, what do you think of? Breaking bones. Bad thing. Bad thing. All right. Medical imaging is their primary use. Okay. Medical imaging. There are many, many different forms of medical imaging, but the original form of medical imaging was X-rays. Okay. So the original form of medical imaging was X-rays. All right. To see bones. Now, X-rays have been around long since before I was ever born. So we all kind of grew up with like, yeah, X-rays, yeah, sure, whatever. But before X-rays, broken bones were kind of a problem for doctors. Because they're like, well, you might have broken it. I don't know. Let's see. And if okay, I think I broke my finger. You know what the doctor would do? He'd take your finger and he'd wiggle it around and see if it wiggled too much. Ouch! That's like torturously painful. Like, let's say you broke it. Wiggle, wiggle. Oh, yep, you did. Oh, okay. And of course, they had less effective painkillers back then too. So it was just like, okay, we're going to torture you to see if this is broken. Okay. And so now you can take as when I was a teenager, I thought I had broken my thumb, so I went and got exactly that X-ray right there that you're seeing in the image. And they looked at my thumb, they're like, nope, not broken. It's like, oh, phew. But from the time I heard it until the time I got to the doctor, I didn't move it. I just kept it nice and still. I put it on a pillow when I traveled in the car. I didn't let it move. I went to the doctor. I set it down like this. They X-rayed it. The X-rays came back. No, it's not broken. I'm like, oh, God. It might have been swollen, but it wasn't broken. I didn't have to move it to know if it was broken or not. Does that make sense? X-rays, kind of nice. All right? Another advantage to X-rays is that once they're like, okay, if it's broken, the doctor, like, for example, if this bone's broken, they'll usually like give you lots of painkillers, and they'll stretch it out and try and get it back in place, because the two ends may have been like separated like this. They want to get it back in place. And then before they put the cast on, they might x-ray it again just to make sure it's in the right place. Okay? So they'll heal better because we now know that they are actually in the right place before we put the cast on it and let it heal. Before, you could have a bone, like if it was a really bad break, and they're supposed to be lined up like this, they might line it back up like this, crooked. And your finger might like twist the wrong direction. Unpleasant, painful, uncomfortable, yes. Okay? So to make sure it heals even better, wonderful technology, x-rays. Now, how do x-rays work? All right? So let's back up for a second to ultraviolet. Skin cancer. All right? Sunburns. This hurts the skin, but it can only go skin deep. X-rays have enough energy that they not only get through the skin, they get through the muscles, they get through all that soft tissue, no problem. But bones stop it. They don't have enough energy to go through bone. So, what you do is you take a piece of film, like camera film from like, cameras before you were born film, okay? You put it down, you put the person's hand over the top of it, and you bombard a whole bunch of x-rays right there on top of it. Wherever the x-rays can go through, the film gets developed and turns black. Wherever the x-rays don't go through, it's undeveloped and stays white. So the thick, dark stuff, that's thick, bone. That's thick, dense bone. The white stuff, the black stuff, that is nothing. And all the tissue, the soft tissue doesn't show, it shows up kind of like a little bit shaded. Does that make sense? So that's how they work. Awesome application. Now, getting x-rays are not dangerous so long as you just get at most like 1 or 2 a year. Much more beyond that, it's kind of like, you really need it? Okay? But even then, they're not that dangerous because they literally only expose the x-rays to you for just a few seconds. So you don't get that much x-ray. Okay? The last one on the spectrum, the last segment of the spectrum. Beyond x-rays, super high energy are gamma rays. All right? Gamma rays, that's the nasty stuff. All right? This is when we're talking about nuclear reactors and nuclear bombs. Okay? We're going to do an entire unit at the end of the semester on nuclear energy, so we'll get into a lot more of the details on that. But for now, just know it's at the end of the spectrum. Okay? So, that right there, the picture, what is that a picture of? Nuclear power plant. Okay? So go ahead and glue that in. All right. Here we go. Now, big picture on the spectrum. Okay? At this end, where the radio waves are two remaining pieces of paper. This is the low energy, low frequency, long wavelength end. Okay? Low energy, low frequency, long wavelength applies to this end. Okay? So your lowest energy, lowest frequency, longest wavelength is radio waves. Microwaves have a little bit more energy, slightly higher frequency, slightly shorter wavelengths. Okay? Radio waves, wavelengths on radio waves can be football fields long. One wave can be more than a football field long. Okay? So really, 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 really long wavelengths. All right? Da, 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 da. On the opposite end, okay, so radio waves, long wavelengths, a little bit less, a little bit shorter, a little bit higher energy, a little bit shorter, a little bit higher energy, as you go all the way up to the gamma waves. Extremely small wavelengths, okay, on an almost unfathomable scale. Super high energy, super high frequency, super short wavelength. Now, in order for this to apply, that the frequency decreases as the wavelength increases, all of these waves have to travel at the same speed. Okay? So all light moves at the speed of light. Now, speed of light should be something that sounds familiar. Ooh, it moves with the speed of light. Okay? Nothing is faster than the speed of light. That number, 3.0 times 10 to the 8 meters per second. Okay? To give you an idea how fast that is, if you had a light wave travel around the Earth, it could travel around the Earth 7 times in just 1 second. That's how fast light is. Traveling around the Earth 7 times in just 1 second. Okay? So to give you an idea, that 1, 2, 3, 4, 5, 6, 7, 8 zeros. Okay? Meters per second. Right? Really, 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 really fast. Okay? Nothing travels faster. All right? A little bit more visual here. Okay? Long wavelengths. All right? Electromagnetic waves, they are transverse waves. These are transverse waves. All right? Over here, shorter wavelengths. All right? Not only are they transverse waves, but they are non-mechanical, which means they can move in a vacuum. They move through the vacuum of outer space. Light moves through space. You probably should know that, just applying that idea of the non-mechanical. They can move in a vacuum. They actually move faster in the vacuum. You put them in air, they move a little bit slower. You put them in water, they move in slower. Okay? Okay? All right. Now, one thing I want to emphasize before we end the journal entry is the idea is to clear up some misconceptions. Okay? This line here between visible light and ultraviolet, I want you to extend that down a little bit there. Okay? Everything from ultraviolet up can cause cancer. Okay? Ultraviolet light can give you skin cancer, but it can't give you liver cancer. It can't give you intestinal cancer because that radiation only has enough energy to get skin deep. Does that make sense? It only goes as deep as your skin and then it stops. So it can give you skin cancer. X-rays, too much X-rays can give you cancer pretty much anywhere in your body because it can kind of get through everything. All right? Gamma rays, yeah, too much exposure to gamma rays can give you cancer. Excessive exposure is more likely to just kill you sooner than that. It's called radiation poisoning. Literally, your cells just kind of start dying, and it sounds gross, but you kind of biologically melt. Okay? It's a nasty way to die, and it's, yeah, fairly quick. Like 24 hours or less, depending on your exposure. Okay? So these can all cause cancer. Excessive exposure to this can cause cancer. These cannot cause cancer. Okay? Your microwave cannot give you cancer. Your cell phone cannot give you cancer. There is not enough energy to do it. Let me explain. Okay? So imagine... All right, so biology lesson. All right, So, biology lesson. What is cancer? Nope. Okay, it's a disease. What causes cancer? Okay, what does the radiation do to cause cancer? It causes a change in your DNA. Okay? Does that make sense? So, for example, ultraviolet light. Imagine this is a strand of DNA. Okay? If it gets zapped by ultraviolet light, it actually snaps the DNA. The cool thing is our cells have these little molecules, these little enzymes that come in and go, oh, wait a second. Those aren't supposed to be apart, and snaps them back together and fixes it. Problem solved. Okay? So a little bit of UV light, not a big deal. One gets snapped, no big deal. Enzyme comes together, put those two ends back together, fixed it. Okay, we're good. Okay? But what if you get exposed to too much radiation? And in one cell, a lot of strands of DNA get snapped. That molecule doesn't know where to connect them back together, and it's going to mix it up. Do you guys see that? The wrong strands of DNA got reattached to the wrong end. Now we have problems. Now we have a change in the DNA. Now we have a cell that's either going to die or turn into cancer. Does that make sense? So, in order for some form of radiation to actually be able to give you cancer, it has to have enough energy to break chemical bonds, to actually break them. Okay? None of these have enough energy to break chemical bonds. They have enough energy to excite them, microwaves. It makes those water molecules vibrate like crazy, but it doesn't snap the hydrogen off the oxygen. Does that make sense? Yeah. So these cannot cause cancer. All right? Am I clear on that? I want to get rid of those, like, oh my gosh, if you're always listening to your cell phone, you're going to get brain cancer. Not true. Okay, now, your cell phone uses microwaves, right? To communicate. If you're talking on your cell phone for a really long time, does your ear get hot? Yeah. Guess what? You're cooking your ear. You're sending a bunch of microwaves through your ear, and it gets warm. It's not going to do any damage to your ear. It's just going to get hot. Okay? Now, I will say, the microwave, your cup of soups, okay? Styrofoam should not go in the microwave. All right? Maruchan, the little cups of soup, that's not supposed to go in the microwave. Because the styrofoam, when exposed to microwaves, lets off chemicals. Those chemicals will go into the food, and those chemicals can cause cancer. But it's not the radiation causing you cancer. It's the radiation in the styrofoam that should have never been in your microwave to begin with. Yes? Don't put styrofoam in your microwave. Only use microwave-safe containers in your microwave. You heat the water up. If you read the instructions on the little Maruchan thing, it actually says heat the water and then add the water to the hot water to the cup. That's okay. Don't put the styrofoam cup in the microwave. Okay? You've been warned. You're young enough. You've been warned. Stop doing it and you won't get cancer from it. Okay? Just warning. All right. So, yes? So, these can cause cancer, the rest doesn't. These all move at the speed of light, 3.0 meters per second, 3.0 times 10 to the 8 meters per second. All right? Low energy, low frequency, long wavelengths, high energy, high frequency, short wavelengths. Yes? You need to know those in order, and you need to know about each one of those sections of the electromagnetic spectrum. Oh, over here. This also applies to the light, the colors of the rainbow. All right? Red. This is your low energy, long wavelength, low frequency light is red. and then orange, then yellow. Okay, so low energy, long wavelength, low frequency. In this end of the rainbow. All right. On the other end of the rainbow, violet. Okay, this is high energy, short wavelength, high frequency within the rainbow. Okay? So this end of the rainbow has shorter wavelengths and higher frequency than this end of the rainbow that has long wavelengths, low frequency. Okay? Cool? All right, that is the electromagnetic spectrum.